Hi everyone, I'm gonna have a look at the question 2 from the week 8 using multi-dimensional version of the Newton's method for solving system of nonlinear equations. So let's have a look at the materials here. We see that the multi-dimensional version of the Newton's method is almost the same as the one dimension. And we see that here by clear clarification, we see that again we have f of x is almost equal to f of x0 plus multidimensional derivative of f of x0 times x minus x0. What the multidimensional derivative of f of x is this one, a matrix of the derivatives. And finally, the aim is to calculating this equation and updating xk plus 1. So let's have a look at the MATLAB code here. We see that firstly we will write the function handle. The function handle comes from the question 2, x cubed minus 2y minus 2 equal to 0. So here x cubed or x1 cubed minus 2 x2 or y minus 2. And for the second and third, we write the equations from the second and third equations here. Now this is the original function for the derivative matrix from the first f1. So we have three functions here. So it will be the derivative of the f1 in terms of the x1, x2 and so on. Depends how many variables we have. And the original function will be a matrix 3 by 1 matrix, but the derivative matrix will be 3 by 3. And the second and third, f2 and f3, their corresponding derivative will be as you see. Now here we define the tolerance. We want to repeat the loop just maximum 1000 times. We have initial value for calculating the derivative, for calculating the xk plus 1. Now here we define error to be tol plus 1, nit equal to be 0, and x vector is at the first we will set it as an initial value for x, and xi will be to be equal x0. And x0, as you remember, we had there. Now here we set fx to be value of the original function at point xi was x0, the initial value. Actually, I mean this one, f of xk. And now for this derivative matrix, we will define it here, which we name it jax. And now here, as usual, we will continue our loop until the error is less than tolerance. And we start the loop by having nit equal to be nit plus 1. And we set the xi to be equal x vector. So nit is the number of the column. And in the first column, we have x0 here because x vector is equal to x0, and as you see that every time x vector, the size of the x vector will be increased. This is one of the features of MATLAB. And here, as I said, this will be the value of the derivative matrix in the point xi. And now since this jax is in the denominator, if it is a very small number, we will stop the algorithm. Now here xn or x to k plus 1 is equal xi minus jax backslash fx. This jax backslash fx, this means like this fraction, the value of the f in xk or xi divided by jax. Now here the error is defined as Euclidean norm of the absolute error, and Euclidean norm is defined here. Here E vect is the is to be equal x vect and error, and every time we will add a column of error to our vect variables, and we renew xi here by calculated xn, and we renew here xi by calculated new xn, and x vect to be equal x vect and xi. After updating xi, we calculate the value of the fx in the new point xi. Once the loop will be repeated, we will use new fx in the calculation of the xn. Now, after reaching the appropriate tolerance, we want to calculate xn. We can calculate xn or x vect. Let's run the code. You see that xn is this one, or we can write x vect, and the last column will be equal to the xn here. We can also have the vect to see the error, or we can just write err. So here also the last column of the vect should be equal to error because of the definition of the vect. And now let's try our solution here. Let's copy this one here, and we will substitute x and y, or x1 and x2, by the solutions that we have obtained there. So we paste here x2, and we reach the 0 error, or almost 0 error, or an epsilon error that we expected. So this means our solutions are true.